Morning, everyone. So, my name's Ankit. I lead genomics business development and strategy at AWS for the public sector globally. Thank you to Nextflow for organizing the summit and for giving us an opportunity to talk. I'll just give a brief overview of what and how AWS supports genomics industry, as well as research, and then sort of leave you guys with sort of a sense of where we are going as an industry, leave you with a challenge, and then later I have my colleague Kevin, who's going to talk about some practical considerations about running Nextflow on AWS. So that's going to be more interesting talk maybe. But let's first talk about genomics, right? I've been at AWS for about 4 years now. And before I joined AWS, I was a staff scientist. I've gone through the rigor of being a grad student postdoc, and then being in the genomic space for over 20 years now. I started back when in 2003, right after the publishing of the human genome, the first publish. And we got a great talk about this from Adam yesterday about the evolution of the whole human genome and the attempts to sequence it. The promise that I started off with back in 2003, I think that promise is still there, right? But it's becoming more and more relevant these days, especially given all the transformative technologies that we have that are pushing the field with sequencing data and on the computing side, where genomics is now considered an important piece of the puzzle when you think about impact on research and population health. Especially coming out of the pandemic, where the sequencing of the viral genome and development of therapeutics against it, the vaccines against it, was critical to us being able to respond to it. Genomics is increasingly being used to understand disease, for therapeutics, for diagnostics, understanding prevalence of disease, and understanding how population evolves, the structure of the population. And this is all being driven primarily because of the access to genomic data. Back when I started, this is a graph. I think the data is readily available on NIH's website. Back when I started, right after the human genome was published, we estimated that you can do a human genome for about $100,000. I'll come to that slide. And then over the last 20 years, we have seen this dramatic 3 orders of magnitude decrease in the cost of whole human genome sequencing, down to where Illumina, as of last year, I think, said you can do a 30x short reads whole human genomes for about $200. And we are finally getting to that stage where you're going to see this inflection point where genomics is starting to get applied not only on the research side, but also in healthcare settings. And that's where I think we'll see this challenge, the challenge that we have in genomics of data, compute, just explode. This is just a short list of various initiatives, consortiums, biobank projects that are going on across the world today that are trying to use genomics in a population setting. This is all across the world. I think this is only about 36. I'm sure I've missed some. T2T and the Pan Genome Project didn't make it up there. But this gives you an idea of how quickly, given the reduction in cost, how quickly population health programs are starting to think about adding genomics as their one of the data sets that they use. To the extent that in the next 10 years, we are estimating that graphic that you saw is just going to expand, it's going to grow. We'll see somewhere close to about 200 plus global initiatives start to use genomics for population health, for research, and increasingly for clinical use cases. And over 100 million individuals will have some aspect of their genome sequenced in the next 10 years. I think there was an estimate last year with a report that said somewhere close to 28 million people have already had some level of their genomes interrogated, whether it's panel sequencing, whether it's whole human genomes, that are exomes or something, right? I think that's going to grow. And this is probably an underestimate. This is 100 million individuals just looking at the growth trajectory that we have. But if the costs continue to come down and genomics starts to get picked up more for clinical genomics, more for the healthcare aspect, that number is going to explode. And assuming, I mean, this is our previous estimate, right? Assuming one person's genome takes about 100 gigabytes of storage, 100 million individuals, that's 10 zettabytes. Who's going to store that? Do we need to store that? Who's going to process it? How do we process it? This is going to be a big challenge. And this is all to enable this flywheel. I come from a research background. I've mostly focused on the right-hand side of this particular flywheel, which is how do we push the boundaries from a research perspective. You look at scientific literature, you look at real-world evidence, you form your hypotheses, you apply those hypotheses, do biomarker discovery, find targets, identify targets for drugs. But then eventually, I think we are going to that, starting to do more and more of this entire flywheel, where these insights are now getting pushed back into healthcare. And we're starting to see precision diagnostics, we're starting to see clinical decision support systems, and personalized care coming out of it. And this flywheel is going to accelerate the adoption and making this challenge even bigger. What we're also starting to understand is while genomics is great and genomics has a lot of potential, it's not everything. It's probably one leg of a multi-legged approach that we need to take if you're thinking about doing precision healthcare, precision medicine. So the entire industry, I think, in some aspect or the other, is starting to move from doing genomics to doing multi-omics to doing multimodal analysis for research in healthcare. Individuals today, I mean, most of us have smartwatches on. We have incredible amounts of data that we are collecting. And every encounter that you have with smart devices, with going to your doctor's office, you're generating data that's important that we need to understand if we need to push the boundaries on what is precision medicine. So individuals today walk around with thousands of data points being collected. And what we need to start to do is we need to start to look at a more holistic view of an individual. Genomics, as I said, is important. It sets the baseline. It also lets us track how the stuff is developing within an individual from a genetics point of view, but it's one aspect. And more, what we are starting to see is organizations starting to collect imaging data, collect clinical encounters, social, geographic data, data from devices and instruments, and start to bring all of these things together. And this is where I think there's still the need for a lot of method development, a lot of algorithm development, approaches for how do you even start to bring these disparate data sets that never have been integrated before. How do you standardize them? How do you harmonize them? And then increasingly, how do you start to apply AI ML approaches? Because Gen AI is the big buzzword these days. But I think that's where a lot of innovation still needs to happen. Are large language models really what is needed, or do you need other approaches from an AI ML perspective? But enabling multi-omics and multimodal analysis, where you start to bring together clinical records, omics data from an individual, imaging data, collecting it, harmonizing it, normalizing it, and then making it integrated so that now you can start to run AI ML models on top of it to generate insights. I think that's the story that the entire industry is sort of moving towards. And so that's sort of from an AWS perspective, that's the thesis that we have on how we are sort of investing to help in the research and the healthcare industry. So AWS works, the way that we develop stuff is through a working backwards philosophy. So the way that works is we see trends in the industry, then we go to the the people who are doing this on a day-to-day basis and try to understand what are their pain points. And then we try to solve for those pain points in that working backwards fashion to come up with those solutions that will move the field forward. So in the last couple of years, we have started to develop purpose-built services, especially for the healthcare and the research industry. Things like AWS Health Lake, which allows you to store health data in FHIR format, store it, transform it, transact it, and analyze it. Things like AWS Healthomics, which is a managed service that AWS put out there that allows you to store, query, analyze, and generate insights from the data. Health imaging, which is sort of the parallel service to Healthomics, but for imaging data, currently for DICOM data, but once again, to store, analyze, and share medical images. And more recently, HealthScribe, which allows you to generate, using GenAI approaches, clinical notes from patient-clinician conversations. And this is all about solving for that common denominator. If you go back to this image that I showed, how do you enable people to collect data, to harmonize data, to integrate data, so that you can finally concentrate on what's important, which is generating insights from the data? I'll give you one example. So this is Roche. I'm sure most of us have heard of it. They needed a platform to unify multimodal health data sets to fuel R&D within their organization to push the boundaries on personalized medicine. And they built their next generation infrastructure, which is called Apollo on AWS. It unifies EHR, imaging, diagnostics, wearable devices, and genomics data together to generate a better, higher resolution view of the individual, of the patient. And this allows them to push the boundaries from a research perspective. And more, I think this multimodal aspect of research in healthcare, we are starting to enable more use cases, more workloads. So whether it's genomics and precision medicine with AstraZeneca, I'm not sure if you guys saw, there was an announcement from the UK Biobank just today. We have there released 500,000 whole genome sequences from the UK Biobank project in their research analysis portal. That was just happened today. And then on the imaging and analysis side, applying machine learning solutions to generate insights across the industry with the Melody platform, using it for virtual screening, for connected labs and knowledge graphs. One thing that I'm very proud of is during the pandemic, Moderna, which uses AWS as their preferred cloud service provider, was able to accelerate their development of their vaccine. They went from getting the sequence back to having a clinical launch within 42 days using the AWS cloud service platform. So the central thesis on the genomic side, and I think on the multimodal side as well, is these were the challenges that we are looking to solve, right? These are the central hypotheses that led to the formation of those healthcare services. People said workflow management is hard, and we are at the Nextflow conference, so I think that's solved, right? But workflow management is hard, and it's extremely challenging to do it at scale, and I think that's one of the things that this room is very aware about. But then there's also this other challenge about integrating across the health spectrum of various data sets. Collaborating on a global scale, I think there's efforts, and I gave you one aspect of it with those global initiatives on the map, but collaborating on a global scale is still a challenge. We are still very siloed in our approaches, and I think that's something that needs to be solved while adhering to the laws and around compliance and data sovereignty. And then, of course, converting data into strategic assets that can then be used across the spectrum is the other challenge. So taking a step back, how does AWS help with research? It primarily starts off with realizing that from a scientist, from a researcher perspective, you don't want to be worrying about servers. you want to be worrying about science. So the AWS Cloud Service Platform allows you to do that. It gives you the access to a wide variety of compute instance types, storage types, so that you use the cloud when you have the need, and then the cloud goes away. And then with projects like the UK Biobank, with projects like the stuff that we're doing with Baylor, the stuff that we're doing with the Allen Institute, initiating, fostering collaboration across organizations, giving you access to data sets that are from other institutions through the Open Data Program, allowing you to leverage and share the effort across various sites where you can containerize workflows and share them. Once again, in this room, I think we're all aware of how reproducibility has always been a challenge in science, and especially in bioinformatics. And that's where I think stuff like workflow orchestration languages and containerization sort of helps to solve the challenge of reproducibility. And then making available the state-of-the-art AI and machine learning tooling so that people can start to focus more on generating insights from the data, all the while built on what is job zero at AWS, which is security. Just to give you a sense of the various different instance types and the workloads that are supported with Amazon EC2, the compute platform at AWS, we have, I think, close to over 100 instance types that support all different kinds of HPC workloads, whether they are HPC optimized, whether they're optimized for compute, whether they're optimized for storage or memory or networking. And then specialized instance types with instances that have the latest state-of-the-art GPUs, or that are specialized for machine learning training, machine learning inference, F1s that allow you to use FPGAs to accelerate genomic analysis. It provides you that flexibility and that scalability that you need when you're trying to push the edge on algorithm development, and then the scalability when you have to put this in production. I'll just give you 3 examples of HPC optimized EC2 instances with the EC2 HPC 6A, which is optimized for basically a lot of different cores with a lot of memory, and being used for compute-intensive applications like CFD and numerical weather prediction, or these EC2 HPC 6ID instances, which have about a terabyte, I think, of RAM, and are being used for those memory-bounded data-intensive workloads. And then the Graviton instances, which are basically our own silicon that we can give you the price performance benefit back that provides low latency, high network performance with the HPC 7G. So there's multiple layers at which AWS allows for enabling HPC workloads in the cloud, right? Starting off with compute and networking, we already talked about EC2 and the networking adapter, but then also how you spin up clusters with AWS Parallel Cluster. How do you get access to fast, efficient storage with Amazon FSx for Lustre? How do you do batch processing? And I think a lot of people in this audience are either using or should use AWS Batch to automate all the workloads. And then at the end of the day, how do you do visualization with nice TCV? This wide variety and the flexibility of instance types gives you that ability to do cost-effective analysis, right? So this is one particular example where working with Sention, we took their FastQ to VCF pipeline and just benchmarked it across all the different various instance types that we can think about, and to process short-read data, 30x short-read data from Illumina for one whole human genome. And I think the best performance that you got was out of the HPC 6A Graviton instance, where this 30x whole human genome went through the entire pipeline, FastQ to VCF, in under 32 minutes with about $1.50 in on-demand costs. And this blog is readily available if you just search for Sention on AWS benchmark. But we have similar benchmarks for Parabricks and other solution providers, even with GATK. So that's just an example of how we are supporting at a very high level research and biomedical research in healthcare. Just to give you a few examples on some success stories. This is a particularly recent one, working with the Wisconsin Public Health Labs, Dr. Kelsey Florek over there. They had built this Nextflow algorithm, Nextflow tool, that they were using at Wisconsin to do some viral surveillance related work at that public health lab. But then there was a need on how do you get other public health labs across the country to adopt this, right? They had already been using Nextflow, but Wisconsin was fortunate in having Dr. Kelsey Florek over there who could run these workloads. Not all public health labs have bioinformaticians within their staff, so the challenge was how do you make this easy? How do you make this simpler that multiple folks without bioinformatics training can run these important workloads? And so through a collaboration between us and a development partner out of Australia called Two Bulls, we built a solution on top of Nextflow Tower called Easy Genomics that leverages those Tower APIs in a simple fashion, in a simple dashboard, allows you to move the data from the sequencers into the cloud and then run Nextflow pipelines on top of it without needing to be a bioinformatician, without having that skill level in there. So it allows you to securely log in to the platform, upload data sets, select the appropriate analytic workflow, which is written in Nextflow, monitor the sample progress using the Nextflow Tower APIs, and receive the results through within the browser or through emails. Another example is the work that's done with the Chan Zuckerberg initiative. This is more of a community effort. It's called the Open Challenge, Open Problems in Single Cell Analysis. So single cell analysis, as most of us are aware, is not a solved problem. There's still a lot of algorithm development that needs to happen. So they built this portal which allows for them to basically put challenges out there for the community to solve, get their workflows, and then run that against the benchmark data and get results out of it that can be then compared, all with a sense of driving innovation in this field. And all of this runs on AWS. So I think running out of time. I also want to leave you with some research programs and initiatives on how we support people getting started on AWS. One of the first ones I want to talk about is our Registry of Open Data, which is a set of genomics and other life sciences data sets that we host for the community for free. So if you ever had the need to basically run against TCGA, against the Kids First data sets, against Nomad or anything, or data from the Sequence Read Archive with the NIH. All of that is hosted on AWS for free for people to use. There's also something called there's an application program. So if you have a data set that you think is a community resource and should be hosted in the cloud, do apply for that particular program, and we'll work with you to basically get that uploaded and made available for the research community to use. And this is part of our AWS Data Exchange. Data Exchange is sort of that marketplace for data. It's a managed service that enables AWS users to find, subscribe, and use third-party data in the cloud. Now, the data in the Registry of Open Data, that's hosted for free, so there's no charge within Data Exchange to use that data. But if you have a data set that you think is an asset and you want to give access to users, but then be able to subscribe in some kind of a financial model, then the Data Exchange also allows you to basically make that available in a secure fashion. The second program I want to talk about is the AWS Cloud Credit for Research. This is something that's existed for multiple years now, but I feel like not many people still know about it. It basically provides cloud credits for researchers, students, postdocs, faculty. When you're thinking about a research project, a proof of concept, and you want to get started in the cloud, you just apply for this particular program. You describe what you're looking to do and provide an estimate of the amount of resources that you need to get started. Then it goes through a review process where it's people like myself, subject matter experts in the field, who understand, who look through the applications and basically approve them. And you get basically credits to get started in the cloud. You also get consultation through our subject matter experts for helping you get started. And then I'm promised this is the last slide, and then you go to questions. But we also launched something called the Health Equity Initiative. This is a program. I think we are going into the third year of the program. So it started at the height of the pandemic, and the idea was, how do we support critical healthcare research that improves the equity that in the healthcare field. I think yesterday Adam gave a good example of how there is a lot of bias if utilizing HG38 only for their baseline analyses, and how that move to the pan-genome with having data sets from multiple ethnicities, multiple population groups, will help solve this gap in equity. I think that's a perfect example of a use case that would and should be supported through the Health Equity Initiative. So we're basically looking for project ideas. We are basically looking for proposals from the community for projects that will increase access to health services, reduce disparities by addressing the social determinants of health, or generating those data sets that fill in the gap that exists out there, especially in genomics, to promote equitable and inclusive healthcare. So this goes through a cyclical research, application process. There are 3 application deadlines throughout the year. It's a global program, and I think the next application deadline is in March 31st of 2024. So if you have an idea, if you have a proposal that you think helps address the gap that we have in the field, definitely do look at it. This comes with not only AWS credits, but also we can support through our professional services for helping you get started on this particular important topic. And yeah, I'll stop with that. I think I'm right around at time. Thank you very much for listening, and thank you for the opportunity.
Thank you, Ankit, for this very comprehensive overview of AWS services. We'll hear more about Nextflow on AWS in about 15 minutes. But for now, thank you very much.
Thank you.